Hello, thank you for watching this video. So in this video we're doing question 10 of November 2022, question paper mathematics paper 2. And the topic is still Euclidean geometry. We might have proportionality and similarity included in this thing. So let's go. They are saying in the diagram, PQR is a cyclic quadrilateral. KP is the tangent to the circle at P. C and D are points on chords PQ and PS respectively, and CD is produced to meet RS at A. CA is parallel to QS, RC is drawn, and you're told that angle P1 is called angle P1 is called angle R2. Let's have a look here. They're saying in this diagram, PQR is a cyclic quadrilateral. PQRS, as you can see here, is a cyclic quadrilateral. So, what is a cyclic quadrilateral? So, a cyclic quadrilateral is a four-sided shape in which all its corners, right, lie on the circumference of a circle. So, all of its vertices, which is P, Q, R, and S, they all lie on the circumference of the circle. So, that's what a cyclic quadrilateral is. That's the definition of a cyclic quadrilateral. So, yeah. And I did teach the cyclic quadrilaterals. If you go to my playlist, check my bad actions, you'll see cyclic quadrilaterals. I did them. I did all of you grade 11 Euclidean geometry. I haven't covered grade 12 yet, but I'm going to cover it very soon. So they are saying PQR is a cyclic quadrilateral. PQR is a cyclic quadrilateral. All of these corners, all of these points P, Q, R, and S, they all lie on this circle. Fine. They are saying KP is a tangent to the circle at P. So you can see KP over there. This line KP, they're saying it's a tangent to the circle at point P. C and D are chords. C and D are points on chords PQ and PS respectively. So, what is it? C and D. So C is here. So C is a point on PQ and D is the point on PS. Right? Fine. CD is produced to meet RS at A. So they're saying CD, where is CD? CD is extended to meet SR at point A. Right? That's what they're saying. So CD, which is this line CD, is extended to meet RS at point A over there. You can see CD, the extension of CD meets RS at that point A over there. They are saying CA is parallel to QS. Where is CA? CA, this length here, this side is parallel to QS, which is this side over there. Fine. They are saying angle P1 is equal to angle R2. They're saying angle P1, where is P1? P1 is this angle here, is called R2 over there. So let me just put that in. Let's say maybe this is X here, that one should also be X, right? Because it should be X because these two are equal. I'm not saying they are X, but I'm just trying to highlight them that this one and that one are equal. So you know what cyclic quadrilaterals, right? So already I said that PQR is a cyclic quadrilateral. So what do you know about cyclic quadrilateral? The opposite angle of a cyclic quadrilateral are supplementary, which means if you were to add this angle and the angle opposite facing it, not the adjacent ones, because these ones are next to this angle. This one is opposite. If you were to add this angle R1 and R2 together with P2, it would be 180 degrees. If you were to add S2 and S3 together with Q1 and Q2, which is this angle and that angle, they make up 180 degrees. Right? No problem. What else can you say? The other thing that you can say is that the exterior angle, which is the outside angle of a cyclic quadrilateral. So if you have a quadrilateral line, let's say you have something like this. Right? So let's say it's A, B, C, D, maybe point E over there. So this angle here and this angle, okay. Angle A plus angle C let's say C1 and C2, that's C1, they give you 180 degrees if this is a cyclic quadrilateral, and it is a cyclic quadrilateral because all of its status they lie on the circumference of a circle. And angle B plus angle D, they also give you 180 degrees, right? Fine. What else you need to know? This angle C2 is called an exterior angle of a cyclic quadrilateral. An exterior angle of a cyclic quadrilateral is between the extension of one side. So you can see DC is extended to E, right? So this length, the angle between this length and the closest side of your quadrilateral is called an exterior angle of a cyclic quadrilateral. So the angle C2 is an exterior angle of a cyclic quadrilateral and is equal to the inside opposite angle, which is the angle C2 is equal to angle A. Those are the properties of your cyclic quadrilaterals. But it's not all of them, of course, but I just mentioned what I think will be applicable to this. If you want more, go to my bed action sessions and watch that video. It should be fine. Fine. So in this case, if you look at the cyclic quadrilateral, PQRS, you can see here, KP is not an this angle P1 is not an exterior angle of this cyclic quadrilateral, right? This P1 is not an exterior angle. Because in order for it to be an exterior angle, it should be an extension of a side. So if this PK was an extension of Q, let's say you were to draw Q straight down, then our PK would be an extension, then therefore it would be an exterior angle. So P1 is not an exterior angle. If you look at S1, S1 is an extension of RS, and RS is extended to A, right? So if you're looking at PQRS, so it's a cyclic quadrilateral, right? And one of the sides, RS, is extended to A. So this angle S1 here is an exterior angle of a cyclic quadrilateral. And an exterior angle of a cyclic quadrilateral is equal to the inside opposite angle. So it's going to be equal to this angle over here. It's going to be equal to that angle over there. So this was Q1. So your angle S1 should be equal to that. So those are some of the properties of cyclic quadrilateral. Fine. Let's go to the real questions now. 10.1. What are they saying at 10.1? They are saying, prove giving reasons that angle S1 is equal to angle T2. So they want us to show that, they want us to prove giving reasons that angle S1 is equal to angle T2. This is what they want us to prove. S1 is equal to T2. Where is S1? S1 is this angle over here, right? And T2 is this angle over here. So they want us to prove that this S1 is equal to T2. Fine. What do we know about S1? S1, which is this angle here, is an exterior angle of a cyclic quadrilateral, just like C2 here. And I said an exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. So which means your S1 is equal to Q1 plus Q2 because the interior opposite angle is all of this angle of the quadrilateral. So which means your S1, angle S1 equal to angle Q1 plus angle Q2, which is that entire angle over there. Why? We'll say this is the exterior angle of your cyclic quadrilateral. Right? That's the first one. So we said this is equal to that. Fine. But we want to prove that T2 is equal to that. So how do we connect this S1 of yours to T2? Fine. But we know that S1 has something to do with Q1 and Q2, right? Because we said S1 is equal to Q1 plus Q2 because the exterior angle is equal to the inside opposite angle. Right? Fine. But look now, if you were to look at Q1, right? If you were to look at Q1, if you were to add Q1 and R2, they would give you S2 because S2, or actually T2, is an exterior angle of this triangle. RTQ. So if you take a look here, your T2, here is your T2, and it's an outside angle of triangle RTQ, right? T2 is an exterior angle of triangle RTQ. And I also did triangles as well. Go to my bad actions. I think maybe like bad action 2 or 3. I did triangles and I did a lot of proofs there. So in that case, I can say in triangle, RTQ, right? If I were to add R2 plus Q2, this would give me, if you add this and this angle here and this angle over here, that would give me an exterior angle. So that would give me T2. This is an exterior angle of a triangle. Fine. Look now, we're trying to prove that this guy over here is equal to this guy. But look now, if we're to write them next to each other, I'm going to write them next to each other. So your angle S1 is equal to, angle S1 is equal to Q1 plus angle Q2 plus Q1 plus angle Q2. That's that. Look at your T2. T2 is equal to R2 plus Q2. They look similar, right? Because if you look at S1 equal to Q1 plus Q2, your T2 is equal to R1, angle R1 plus angle your T2 is equal to angle R2 plus angle Q2. So, in a way, if you were able to show that your R2 is equal to Q1, you will have proven that these two things are equal because they would both be equal to the same stuff. So if you're able to show that this is Q1, then this will be identical to that. Therefore, these two things will also be equal. And that would finish your proof. So what we need to prove, let's try to show that this is equal to that, which is your Q1 is equal to your R2. So what is Q1? Q1 is this angle here, right? And where is your R2? R2 is that angle over there. What do we know about R2? We were told on our statement, remember on our statement, they told us that R2 was equal to, because we look at place X, they told us that R2 is equal to P1, right? This was given information, we were told this thing. No problem. Then what else can we say? Remember that P1 is this line over here, and this line is a tangent to the circle, right? KP is a tangent to the circle at point P, and you know, if you watch my one of my bad actions, maybe the last ones when I was doing tangents, I did the Tan-Chord theorem there. So the Tan-Chord theorem, just to remind you, it says that if maybe you have some sort of a circle like this, let's say you have a chord somewhere. Let me place the chord here. So, and you have a tangent at the point of contact of the, you have a tangent, right? And your end point of your chord meets this tangent here. So that's saying the angle between the tangent and the chord will be equal to the angle that this chord will subtend on the other side. So this angle here will be equal to that angle. If this tangent subtends another angle there, if this chord subtends another angle there, that angle will also be the same. So the angle between the tangent and the chord is equal to the angle that the chord subtends on the other side, right? In a similar way, this is a tangent and this is a chord as well. Let's say this is angle beta. So now the angle between the tangent and this chord of yours is equal to the angle that this chord subtends on the other side. So this should be beta as well. That's how the Tan-Chord theorem works. So now, if you look here, here's your P1. So P1 is between the tangent and this chord here, PS, right? So, which means the angle between the tangent and this chord, which is your P1, is equal to the angle that this chord subtends on the other side. So what happens is that the angle between the tangent KP and the chord SP is equal to the angle that this chord will subtend on the other side. So what that means that your P1 is equal to Q1. So which is your P1, angle P1 is equal to your angle Q1. Why? Because of the Tan-Chord. So because we have a tangent, KP, and you have a chord. Your chord is SP. Right? Look now, your R2 is equal to P1, and your same P1 is equal to Q1. If your RP2 is equal to P1 and your P1 is equal to Q1, then which means these two are also equal. So therefore your R2, angle R2 is equal to your angle Q1. So that's the transitivity property of equality, but you don't have to reason for that. So now look now, we have proved that these two things are equal. Therefore we can say now, therefore I'll write this and say S1, right, is equal to Q1. What is your Q1? Your Q1 is equal to R2, which is R2 plus Q2, right? And then your T2 is equal to R2 plus Q2, which is this is equal to this, and this same thing is equal to that, which is these two things are equal in a similar way. Is that therefore your angle S1 is equal to your angle T2. So which means this angle here, let's say maybe I'll call it Z, is equal to this angle right here, right? And this angle here, we said P1 is equal to Q1, right? That's what we do. That's what we did. Wait, what? Yeah, P1 is equal to Q1. That's Tan-Chord, right? P1 equal to Q1. So this should be X, this angle here. This angle, this one is X, and this one is Z. Fine. So maybe we'll call this one Z as well. That's to indicate the things that are more or less similar or equal, sorry. Now I'm going to move to 10.2. Okay, so now we're doing 10.2. They are saying at 10.2, prove giving reasons that AD over AR is equal to AS over AC. So they want us to prove giving reasons that AD over AR is equal to AS over AC. So, what are these things? So AD over AR is equal to AS over AC. So where is AD? AD is this length over here. Is your AD. So I'm going to write it maybe inside here because it's this small part. It's not the entire thing. So here's AD over AR. Where is AR? AR is the entire length there, right? So AR is this length here. So AR. AR. AS. Where is AS? AS is this small length here. So I'll write it inside here. AS. The small length from here to here, okay? What else? AC. Where is AC? AC is the length from here to there. So it's this entire length from here to there. So we're calling it AC. Okay. So which means we're saying AD, which is AD over AR, is equal to AS over AC. Okay. No problem. So you can see that both of these things, they involve the smaller parts, which is the smaller part of this triangle here, and the big part of the triangle, that one. Right? So your AS's, your AD and your AS belong to the small triangle, and your AR and your AC belong on the big triangle. So what they did, they said, okay, your AD and divided by the entire length of that side, and say AS and divided by the length of this side. So let's say, let's suppose this is not the case. I'm just trying to see what will work because there's no straight formula for these things. This is the kind of stuff that you figure out on the way, in my opinion. That's how I do them. Because I don't know how to relate this. Of course, you will use the properties that you have or the equipment that you have, which is your Euclidean geometry principles, you will use your proportionalities, you will use your similarity rules that you know, right? Fine. So what do we do now? Let's say in triangle ACR, right? Let's say this is triangle ACR, right? And let's say this SD was parallel to RC. Let's say SD was parallel to RC. So I'm not saying this is the case. I'm just trying to find in which way are these things related, right? In which ways are these things related? So if this is parallel to that, I can apply my proportionality theorem and take the ratios of these corresponding sides that I have. So I'll say, if SD was parallel, this is not, I'm not saying we should write, like, this is a way of writing it. You must try to relate these things. So I'm going to assume first that SD is parallel to, okay. So I'm assuming that SD is parallel to CR. Then I'll say, okay, in triangle, ADS maybe, and triangle ACR, right, in these two triangles. What am I going to say? In these two triangles, I'll say, okay, if this is parallel to this, I'm assuming I've made this assumption because I want to see if we can get this relationship from proportionality. So if I'm saying this is parallel to this, I'll try to apply the proportionality theorem. Now, one will ask themselves, what is the proportionality theorem? So let me clean the board and then do a small refresher of what a proportionality theorem is. So we're going to try to we'll do a small refresher of what a proportionality theorem means. All right? Okay. So how are we going to do this? So we're trying to revise proportionality theorem. Fine. So let's suppose that we have a triangle here. We call it ABC, right? And this triangle is divided by a line, maybe DE, and that line is parallel to the third side, right? So you have triangle ABC, and that triangle line ABC, two sides are joined by a line segment DC, and that line segment is parallel to that side. That's like if you have this condition, what you have here, the ratio of the corresponding parts will be equal, which means if you take the top part, which is AD, and divide it by the bottom part, which is DB, it should be the same as AE, right, over the entire side AC. This is not the only ratio that is true. As long as you take the ratio of the same parts, the proportionality theorem will always work. Those ratios will always be equal. For example, I said the top part over the bottom part is equal to the other top part over the bottom part. If I can say the top part, which is AD, over the entire side, AB, it should be the same as the top part, the other side, which is AE, over the entire side, this side, which is AC. It doesn't matter which parts. You can say this part over the entire side, say this part of the entire side. They will be equal as long as you take the ratios of the same parts. So that's what I'm trying to do here. This assumption that these two are parallel, this and that are parallel, I want to apply the proportionality theorem. I want to take the ratio of the corresponding sides. And the sides that I'm going to take are the sides that I have here and see if they will be giving us an answer similar to this. Okay, no problem. How do we go about this? We say, okay, now, since we assume that this is parallel to this, so this line now in this case, which is this, I'm assuming that your ds is parallel to that, right? So if your ds is parallel to that, you can apply a proportionality theorem. Let me put these proportionality signs. So I'm saying I'm assuming this is parallel to that. So now if you take the ratios, it's going to be as, right? Going to be as. We can say SR, but there's no point of using SR because we don't have SR here, but we have AS and AR, and we have AD and the entire side AC. So if we can take this AS and divide it by the entire side, which is what? Which is AR, it should be the same as the AS, which is the small part over the entire side, should be equal to the small part here, right? Should be equal to the small part AD over the entire side AC, which is AD over AC, right? That would be our proportionality theorem. But look now, we have AS, there is AS, we have AR, AD, AC, AC. What is the problem? The problem is that AS is divided by AR here, but AS is divided by AC. AD is divided by AR, but OD is divided by AC. So this and that are not equal, and you cannot make them equal. So this is not the same thing as that. So this assumption that these two things are parallel, it will not work because they are not parallel, it seems. So I'm going to take this back. I'm removing that parallelness. These two things are not parallel. I was testing to see what would happen if they were parallel. Right? Fine. So I'm going to clean this green thing here. So these two things, proportionality theorem does not work. So what we're left with is similarity now. Okay, so now that we have seen that proportionality didn't work very well, what we should try to do maybe is apply similarity and see if it works, right? So they're saying the ratio of AD to AR is the same as the ratio of AS to AC, right? No problem. So what are we going to do here? So look at AD, right? Look at AD. So starting to A to D. Where is A? Is A, is D. Where is D? Is D. So we can say this is point number 1 maybe, and this is point D, point number 2, right? Point number 1 and point number 2. And then now, let's look at AR. AR, I'm not sure, it may be on the big triangle or the small triangle, right? But if it's on the big triangle, I would think it's a corresponding part of AD. Let's go and look for AR. AR, here is it, AR. So, which is A is also number 1 and R is also number 2. So A is 1 and R is number 2. Right? So you have AD over AR. So what I would like to think of this as, I would like to think of this as AD. AD is a corresponding side of AR, or is corresponding to AR on the other triangle. Right? Which is your AD of the small triangle is represented by AR on the bigger triangle. So if you're looking at these triangles now, you'll be looking at triangle ADS and triangle ARC maybe. So let's say in triangle ADS and triangle, I said in triangle ADS. So what is AD represented by? It's represented by AR there. So this will be triangle ARC and triangle ARC. You can see your AD. Your AD is sitting, and AD and AR, they are both sitting in the same position. Look at AS. Your AS is this, and it goes together with AC. Look at AC. So your AD, which is the first letters, over your AR, the second letters, is equal to your AS over your ACs. So if we can prove that these two triangles, which is the triangle ADS and triangle ARC are similar, then we'll be able to express this ratio. So I think what you need to do, you need to prove that this triangle and this triangle are similar. Once you prove that they are similar, then we'll be able to apply this ratio. So that's what we should try to do, it seems. So what does it mean for two triangles to be similar? So the two triangles are called similar if they are scale division of each other. So let's say you have two identical triangles. One will say they are congruent, which is correct, but one will say they are similar, which is also correct. So all congruent triangles are similar, but not all similar triangles are congruent. Because being congruent means they are identical. Being similar means they are scale division of each other, which may be equal or not. Right? Fine. So how do we check if two triangles are similar? So I haven't done lessons at least to date, but if you want to prove that two triangles are similar, you must show that at least two of the corresponding angles, they have at least two equal corresponding angles, or the ratios of the corresponding sides are equal. So in these two triangles, if we can show that angle A is equal to angle A there, angle D is equal to angle R, or angle S is equal to angle C, then you have proved that these two triangles are similar. You don't have to prove this angle is equal to this angle is equal to this angle is equal to this. You don't have to prove all of them. You can just show that these two are equal to these first two, or these two is equal to this other two, and these equal to those. That will do the work. Just show at least two pairs of corresponding angles, then you'll be fine. So you don't have to show all of them. So if I can show angle A is the same as A, angle D is the same as R, and angle S same as C, then we have shown that these two triangles are similar. That will be enough. You don't have to go and check the third one. But you can if you have all the time. But I don't think we have a lot of that. So let's try to prove this. Look now, angle A and angle A. Let's go and look at that angle A of this triangle. Where's ADS? ADS, so this triangle here. And then where's the other one? ARC. ARC. You can see that this angle is in both of these triangles, because look at this angle here. ADS, here's your ADS, triangle ADS. So you can see this angle. And look at your ARC. ARC. It's the same angle. So this angle is used twice. So it's in both of those triangles. So it's okay. Angle A of this triangle is called angle A of the triangle. Why? This is a common angle. So they are sharing this angle. Fine. No problem. So now, what we can try to do maybe to show that angle D is called angle R, or angle S is called angle C. Where's angle D? Angle D is this. Angle R is that. I didn't use any of these two things. I don't remember using this or that. But I remember something about S, because remember, on the first question we proved S1 is equal to T2. Prove that S1 is equal to T2. Right? So at least we have one angle here. Angle S, which is this angle S here. If we can prove that angle S is equal to angle C, would be okay, because at least we would have proved that two pairs of corresponding angles are equal. Then we'll be done. Right? Fine. So what do we do now? We would like to show that this angle here, angle S, which is this, is equal to angle C. We know that angle S is equal to angle angle S1 is equal to angle T2, which is what we proved there. How can we relate angle T2 to S? But if you look at them, this is a parallel line, your QS is parallel to CA. If you look at this angle C2 and angle T2, they are alternate angles on parallel lines. These are alternate angles. So alternate angles on parallel lines are equal, which means your C2 is equal to Z as well, which is equal to T2, which is Z. So in that case, you will have that this angle is equal to that angle, which is you have A equal to A and your S equal to C, which is enough to say these two triangles are similar. So what we'll say was, okay, S1 is equal to what? S1 is equal to T2. We proved this. Where? At 10.1. Fine. Done this. And then now, we're proving now that T2, the T2 now is equal to your C2. Why? These are alternate angles, right? On parallel lines. Because your QS is parallel to CA. So look now, your S1 is equal to T2. Your T2 is equal to C2, which is your C2 and S1 are the same as well. Because if two things are equal to the same thing, they should be the same as well. Or they should be equal as well. You can say, look, S1 is equal to T2 and the T2 is equal to C2. Therefore, your S1 is equal to your T2, which means your S1, which is this angle S1. Actually, sorry. I said S1 is equal to T2 and T2 is equal to C2. Therefore, your S1 and C2 are also the same. So in these two triangles, you have that angle A is the same for both of them. Your angle S1 is the same as C2. So these two triangles are similar by angles, which is all their angles are equal. Which is this angle is equal to this one is equal to this one, and this one here is equal to that one over there. So we can say, therefore, triangle what? AGS, the order is important, is similar to triangle ARC by angles. All the corresponding angles are equal. Therefore, if these two triangles are similar, the ratio of the corresponding sides are going to be equal. Which means, look now, you're given what AD. Where is AD? AD is this. So your AD over AR should be the same as AS. AS, first and last, which is AC there. Right? Which is what they want to prove. Also, just to be extra, which is your DS is equal to your RC. So it means, but you don't have that. You just need the first part. But you need, in order for you to do this, you need to show that these two triangles are similar. And they are similar. Therefore, the ratio of the corresponding sides are going to be equal. And we're done with 10.2. Okay, so now we're doing 10.3. So at 10.3, they are saying, prove giving reasons that AC times SD is equal to AR times TC. So they want us to prove this thing over here. AC times SD is equal to AR times TC. Fine. What do we know so far? So far we know this. We just proved this, right? And that we extrapolate that. We didn't have to. But look now. Your AC over here. You can see this AC. Here is it. There is AC. Here is it. Your AC. Here is your AC. Your SD. Here is your SD here. Your AR. Here is your AR. Your TC. You don't have TC. You don't have your TC. AD. You don't have AD. AS. We don't have AS. RC. We don't have RC. So what do we do? Look, you have this and this and that. 1, 2, 3. These three are all shown here, right? If I were to look at AR and AC, AR and AC are on the different side of this, right? AR and AC. Yeah, they're on the different side of this. Right? They are multiplying other stuff. Then, okay. I have AR and AC. They are multiplying other stuff. If I were to multiply, if I were to cross multiply here, I would have AC maybe over AR is equal to AC over AR is equal to AS over AD. But now I'll be having a ratio of this and that. But that's not what I want really, right? Okay. It's fine. That's what we're getting here. But look on this side. Look at AC and DS. If you can cross multiply, say this times this, you get AC and DS. AC and DS are this. On the other side, you will have AS and RC. But you don't have both of these things. But at least you would have this, right? Which is half the thing that you want. Because if you have AC times DS, you have one side. Now you'll be trying to hunt the other side. So we can say, we can take this and say, AS over AC is equal to DS over RC. So let's be clear that this had to go. We like this. We like this. This had to go as well. So I'm using this because of these are corresponding ratios of similar triangles, right? So now let's cross multiply. This time that we'll have AS times RC is equal to AC times DS, right? Times DS. So both of these guys have to go, you can see, and we like this, we want to keep them. Fine. So if you look at our thing, we want to prove that this is equal to that. This we have is this one. If you can try to find AR and TCs, if you can be able to find AR and TC and maybe equal to the same thing, then we'll have proved that this is equal to that. Because we have AC and DS equal to this. If we try to find this to be equal to this and that, these two will be equal. Fine. We need something to do with AR and TC. Where is AR? AR is this entire length here. Where is TC? TC is this small length over here. So TC is this length over here. So look now, what you have. You have a triangle ARC and maybe triangle ASD. Okay, let me start that. You have a triangle ARC. A triangle ARC. What? Okay, let me start this again. You have triangle RST and triangle RAC. So you have two triangles. Okay, actually, you have one triangle RAC. And this triangle RAC is divided by the line segment ST. And your ST is parallel to AC. Therefore, you can apply a proportionality theorem, which I explained on the other side when I was assuming this, when I was doing some assumptions here. So, you have triangle RS, you have triangle RAC that is divided by ST, such that your ST is parallel to AC. Therefore, your proportionality theorem will work, which means you can take the ratios of the corresponding sides and they will be equal. That's what we'll try to do. So, what do we do? It's okay. What do? We say we want to have something to do with what? With TC and AR. Okay. TC is this small part, right? AR is that big part here. So this small part corresponds to the other small part. And we want to have a big part which will correspond to the big part here. So if we say maybe your small part AS over the big part AR is equal to TC over the big part RC, right? Because that's how this will work, because we want to have this small part and that big part. So if we're using proportionality theorem, we're going to have to take the ratio of the same parts, which means this part over the entire side is called this part over the entire side. So what we have is what? We have, what do we have? AS, or actually, it's going to be maybe AS over AR, which is this small part over the entire side, which is your AS over your AR is equal to your CT over CR. So I said this small part over the entire side called this small part over the entire side. So I was saying this is proportionality theorem, right? This is a proportionality theorem because your AC is parallel to ST or maybe QS, I don't know. So if you look at this, AS, we don't want AS because we don't have AS there. AS, we don't like it very much. AR, yes, we do have AR, we like AR. CT, yes, we do have CT. CR, no, we don't have CR. Right? There's no CR there, so we want to get rid of it. So let's cross multiply this. So if you cross multiply this, get that your AS times CR is equal to your AR times CT. So which means these are the guys that you don't like, these are the guys that you like very much. AS times RC, AS times RC. So this and this are exactly the same, which is these two are also going to be equal as well. Because if this and this are equal, they are both equal to other things. Those other things should be equal. You can say therefore, AC ds is equal to AR times CT. That's what we have. And we're done with this question. And I hope it does make sense to you, as it does to me. Thank you for watching. Cheers.